Okay, I have a little bit of a headache setting in, so I'm going to try and get through this before it gets too bad. We are going to be doing free body diagrams and Newton's second law. So this is primarily about translating a free body diagram into a second law statement and getting something useful out of it. I'm actually going to use some things that we've talked about or that you've done on quizzes or that we've done other places as examples. So the first one here is we have had a problem where there were two masses, mass 1 and mass 2, hung by ropes from some surface. If we're thinking about these, the forces that would act on them, we'd have a tension 1 at the top, a tension 2 in the middle. So there would be a tension 1 supporting, a tension 2 acting down, and the weight of this object acting down. Now, since it's hung from a surface, unless one of those tensions breaks, we know the acceleration would be equal to 0. Okay, if you're having trouble figuring out which forces count, do a quick little box around it. Only things that touch that box and field forces like gravitation will still be able to act on it. Okay, looking at the bottom one, mass 2. If we do our little box around it, it becomes obvious there's really only the tension 2 acting upwards this time, and the weight m2g acting downward. Acceleration would still be 0. Alright, Newton's second law states that the sum of forces is equal to ma. So in this case, acceleration is 0. T1 minus T2 minus m2g equals 0. I say minus because they're acting downward and I'm explicitly setting the sign for them. More properly, you may want to consider that, well, it's g is a downward acting acceleration. So m times the gravitational acceleration is going to be a m times minus g. It would be acting downward. The tension is harder to see, but the tension just redirects the force in this case. All right, for mass 2, we'd be able to say T2 minus m... crud. I made a mistake. We were talking explicitly about mass 1 here. This should be mass 1g, not mass 2. In the second equation on the bottom, it is mass 2g. All right, the main thing we get out of this is from the first one, T2 must be equal to just the weight of the second one. And if we substitute that back up, T1 must be equal to m2g, which comes from our T2, plus m1g. Okay, so this is how you can get something useful out of free body diagrams and Newton's second law. All right, while we're talking about it, a classic problem that I don't think we do any of these in this class, although there is something I can do with buoyant force related to this, which is kind of a cool problem. But you're definitely going to see it in a future physics class, is inclined planes again. So let's imagine you have some kind of inclined plane. And we put some box on it. And I'm not going to worry about friction here, so we're just going to put our box on it and say it has some mass. We'll make this have an angle theta down here, and we want to figure out how would this box move. Well, the first thing to point out is when you're doing a problem on an inclined plane, it's usually a good idea to set your coordinate system up in such a way that one of the axes is aligned with this perpendicular direction. So here I've set things up so y is perpendicular to our axis. What that gets us is the acceleration along that y must be 0. And ax will give us our acceleration. That will be the part that actually accelerates. Okay, if we think about the forces that act on this, there will be a normal force that will be perpendicular to the incline. There will be a gravitational force that acts straight down, and that's actually it. So one of these forces is responsible for creating the acceleration along the incline, and it is gravitational. But that means we need to split up gravitational into components. A component that's along our tilted y-axis and another component that's along our x. Now to figure out how that's going to go, consider that the gravitational force is going to act along this line, which means this angle up here is actually known to us. It would be 90 minus theta. And if we drop a perpendicular through here, we know that this must make a 90-degree angle with the inside or with the upper surface of the triangle. So this whole thing adds up to 90 degrees, which means this is 90 minus theta, or theta. All right, tricky thing to remember, but that means this angle in here is also, and I drew it kind of too small. I'll cheat a little bit. But this angle is also theta. Okay, so when we split this up, we're going to get one component that's adjacent, mg cosine theta, and another component that is opposite, mg sine theta. So our result will be, vertically along y we have n minus mg cosine theta equals 0. So the normal force is not mg, it's just a part of mg. It's mg cosine theta. Okay, sum of forces on y and sum of forces on x. On x, we literally just have mg sine theta, and that will be responsible for ma. So now we can state the acceleration would look like g sine theta. All right, so I have a worksheet prepared. The front page of this worksheet has you do free body diagrams for several simple cases. The back side is actually the answer key for the front side. On the back side, you take those free body diagrams and you turn them into Newton's second law equations like I have here. And that's just practice 8 cases of drawing diagrams and then getting equations out of them. We do use this sort of stuff quite a lot. The sum of forces equals ma, or the sum of forces equals 0, is a very common motif for how we both derive equations in Physics 1b and how we solve problems in Physics 1b. So give that sheet a try. I believe I also have a third page at this point, which has some answers for the second page, and then I think it has a few more problems for you to try. And they're just word problems at this point, so you have to make everything up for yourself. So give those a look. Hopefully they'll help you straighten things out and get things working better before we use forces for too much. All right, I'm going to stop here, and I guess I'll probably be recording torque videos next time I have time.